Imagine leaving the Milky Way behind, venturing into uncharted galaxies, traveling through wormholes and cosmic gateways. From black holes to warp drives, humanity's dream of intergalactic exploration pushes the limits of physics, technology, and imagination. Could we survive the journey and what awaits us beyond our galaxy? For as long as humans have gazed upward, the stars have whispered questions we cannot fully answer. Early astronomers charted constellations, imagining them as maps, guides, or divine signatures. They marveled at the Milky Way itself, a river of countless stars stretching across the night sky, a reminder of how small and fleeting our existence truly is. Each flicker of distant light inspired wonder, curiosity, and the urge to reach beyond. Centuries later, our dreams took shape in stories, in myth and fiction. From Jules Verne to modern science fiction, humanity envisioned ships sailing through the cosmic ocean, escaping the confines of our solar system, even venturing into the uncharted territory of neighboring galaxies. We imagined the thrill of first contact, the discovery of alien worlds, and the awe of traversing realms that defy comprehension. Yet beneath the fantasy lies a question that persists. What would it truly take to leave the Milky Way? The emotional pull of intergalactic travel is profound. It is not merely the pursuit of knowledge, it is the pursuit of survival, ambition, and legacy. To leave our galaxy is to confront the immensity of space, to challenge the limits of our technology, and to wrestle with the philosophical weight of becoming a species unbound by a single star system. Tonight, as the Milky Way arcs across the heavens, we are reminded of both our fragility and our audacity. We are creatures of curiosity, yearning to push beyond the familiar, to traverse distances so vast they strain our imagination. This is not just science. It is a story of human desire, courage, and the eternal drive to reach the impossible. The dream of leaving the Milky Way has captured our minds for centuries, and now, we stand at the threshold of contemplating it as more than fantasy. Understanding galactic scales. To grasp the challenge of leaving the Milky Way, one must first understand the staggering scale of the galaxy itself. Our home is not just a cluster of stars. It is a sprawling spiral of over 200 billion suns, stretching roughly 100,000 light-years across. Imagine standing on a mountaintop, looking out over Earth, and then multiplying that view by billions. Each point of light in the night sky represents a star system, many with planets, some perhaps harboring life, and all separated by incomprehensible distances. The Milky Way is surrounded by an even larger halo of dark matter and scattered gas, invisible to our eyes but accounting for a significant portion of its mass. This invisible scaffold shapes the galaxy's rotation, keeping stars on intricate orbital paths. Within this cosmic city, our solar system is a tiny suburb orbiting a quiet, middle-aged star at an unassuming pace of roughly 828,000 km/h. Yet even at that dizzying speed, reaching the galaxy's edge would take tens of millions of years with conventional propulsion. Consider the nearest galaxy beyond our own, Andromeda, over 2.5 million light-years away. To travel that distance, light itself, the fastest known entity in the universe, takes more than 2 million years. If humanity attempted the journey with current spacecraft technology, the voyage would span countless human generations. It is not just a matter of speed. It is a matter of endurance, energy, and survival across cosmic expanses where time, radiation, and gravity pose constant threats. Visualizing these scales challenges our intuition. Picture the sun as a mere grain of sand in a vast desert. Even our nearest stellar neighbor, Proxima Centauri, would be several kilometers away in this metaphor, and the edge of the galaxy would stretch beyond the horizon of any conceivable journey. Distances that seem abstract in numbers, light-years, parsecs, kiloparsecs, translate into an almost unbridgeable gulf when imagined physically. Yet, understanding these scales is not meant to deter us. It is meant to inspire. The enormity of space illuminates the audacity of human curiosity. Leaving the Milky Way is not a small ambition. It is the ultimate test of ingenuity, courage, and the desire to reach beyond the familiar into the truly unknown. The speed limit of the cosmos, in the vast arena of the universe, nothing moves faster than light. This immutable limit, dictated by Einstein's theory of relativity, is both a boundary and a tantalizing challenge for humanity's intergalactic dreams. Light travels at 299 through 792 kilometers per second, an almost incomprehensible speed, yet even at this velocity, it would take over 2.5 million years to cross the void between the Milky Way and our nearest galactic neighbor, Andromeda. For a civilization bound by lifespans measured in decades or centuries, the cosmos remains staggeringly distant. Einstein's equations reveal a sobering truth. As an object approaches light speed, its mass increases, demanding ever more energy to accelerate further. Conventional propulsion, chemical rockets, ion drives, even nuclear engines simply cannot overcome this barrier. Humanity's fastest spacecraft, like Voyager 1, would need tens of millions of years to exit the solar system, let alone traverse the galaxy, and the Milky Way itself spans 100,000 light-years in diameter. The gulf between ambition and physical reality is monumental, yet physics also hints at possibilities that seem almost magical. Concepts such as warp drives, first theorized by Miguel Alcubierre, suggest that space itself could be manipulated, contracted in front of a ship and expanded behind, to achieve effective faster-than-light travel without violating relativity. Wormholes, hypothetical tunnels through space-time, could, in theory, connect distant points instantly, bypassing the speed limit entirely. But these remain speculative, requiring exotic matter, negative energy, or conditions beyond our current technological reach. The universe's speed limit forces a profound humility. Every plan for intergalactic travel must contend not only with engineering challenges, but with fundamental cosmic laws. Time dilation, relativistic effects, and the relentless passage of energy all conspire against conventional exploration. Humanity cannot simply push harder. The cosmos enforces its own boundaries, and yet it is precisely this limitation that ignites imagination. For every barrier that physics imposes, there is a spark of ingenuity, a question of how to bend, circumvent, or reinterpret the rules of reality. Leaving the Milky Way may be impossible today, but understanding the speed limit of the cosmos frames the ultimate challenge: to expand human reach while respecting the vast, unyielding tapestry of space-time. Wormholes, nature's cosmic shortcuts. Imagine a tunnel through the fabric of space itself, a bridge that bends the universe so that 2 points light-years apart can touch. This is the tantalizing promise of a wormhole, a concept born from Einstein's general relativity, where gravity curves not just space, but space-time. While stars and planets create gentle dips in this cosmic fabric, a wormhole would fold it completely, connecting regions of the cosmos in a way that defies ordinary intuition. The idea was first formalized in the 1930s by Einstein and Rosen, who described bridges linking distant points, later termed Einstein-Rosen bridges. Unlike warp drives or faster-than-light propulsion, wormholes do not accelerate objects beyond the universal speed limit. They simply shorten the journey. Step through one end and instantly emerge elsewhere. In theory, this could turn a 2.5 million light-year trek to Andromeda into a journey of moments. Yet the elegance of the theory collides with daunting challenges. Classical wormholes are inherently unstable. Left alone, they would collapse in a fraction of a second, pinching shut before anything could traverse them. To hold one open, physicists hypothesize the need for exotic matter, material with negative energy density. Such matter could counteract gravitational collapse, creating a stable corridor. While exotic matter remains hypothetical, quantum physics hints that the universe might allow fleeting glimpses of it, fleeting opportunities for a cosmic shortcut. Wormholes also raise staggering possibilities and risks. A traversable wormhole could connect not only distant galaxies, but even different eras of time, producing mind-bending paradoxes. Navigation would require understanding the curvature of space-time with unprecedented precision. Miscalculations could strand travelers in the void or near the singularities at the throat of the bridge. The cosmic scale and energy requirements push the concept far beyond current technology, but they do not render it impossible in principle. The allure of wormholes lies not only in their utility, but in what they represent, a path through impossibility. They embody the idea that the universe is not a flat map of dead distances, but a dynamic, foldable canvas where geometry itself might become a vessel for exploration. Scientists continue to study their mathematics, simulate their physics, and search for indirect evidence in gravitational waves or distortions in light from distant stars. Each discovery refines our understanding of whether these bridges are a theoretical curiosity or the ultimate route to leaving the Milky Way. In contemplating wormholes, humanity confronts the limits of imagination, physics, and courage. The cosmos may be vast beyond comprehension, but wormholes whisper of a daring truth. Even the greatest distances might one day be bridged. The science behind wormholes, beneath the cinematic allure of wormholes lies a web of complex physics, where the very fabric of reality is stretched and contorted. Traversable wormholes are not merely holes in space. They are solutions to Einstein's field equations that require conditions alien to everyday experience. To hold open a tunnel connecting distant points in spacetime, conventional matter simply won't suffice. The solution proposed by physicists is exotic matter, a substance with negative energy density, capable of counteracting the immense gravitational forces that would otherwise collapse the wormhole instantly. Negative energy is not entirely theoretical. It emerges in quantum phenomena, such as the Casimir effect, where vacuum fluctuations create measurable forces between closely spaced metal plates. Yet scaling this microscopic trick to a macroscopic wormhole is an entirely different challenge. The amount of negative energy required, the precision of its distribution, and its stability remain beyond current technology or practical experimentation. Mathematical models of traversable wormholes reveal both hope and peril. In theory, a wormhole's throat, the narrowest part of the tunnel, could remain open long enough for matter or spacecraft to pass, provided the energy distribution is maintained perfectly. Even a slight imbalance could trigger a catastrophic collapse, producing singularities akin to black holes. Scientists use general relativity and quantum field theory to explore these scenarios, creating simulations that test the boundaries of possibility, yet all remain speculative. Additional challenges include tidal forces, time dilation, and causality paradoxes. Traveling through a wormhole may expose a spacecraft to gravitational gradients intense enough to spaghettify anything unprotected, while differences in time flow between the two mouths could create strange temporal effects. Moreover, wormholes could theoretically allow time travel, raising profound questions about paradoxes, causality, and the very structure of spacetime. Despite these obstacles, wormholes remain a tantalizing frontier. Their study stretches human ingenuity, forcing scientists to combine relativity, quantum mechanics, and theoretical engineering in ways never before required. While we are far from building one, understanding the physics brings humanity closer to conceiving what intergalactic travel might demand. Wormholes sit at the intersection of imagination and rigorous science, a reminder that the universe is not merely observed, but actively tested in the mind, where physics and possibility converge, and the dream of leaving the Milky Way inches toward plausibility. Black holes and cosmic gateways. Black holes have long captivated the imagination, standing as the universe's ultimate enigmas, regions where gravity curves space-time to extremes beyond comprehension. At their core lies a singularity, a point of infinite density where the known laws of physics collapse. Surrounding this abyss is the event horizon, the boundary beyond which nothing, not even light, can escape. While they seem like cosmic endpoints, black holes may hold the key to one of humanity's most audacious dreams: shortcuts across galaxies. The theoretical link between black holes and wormholes emerges from solutions to Einstein's equations that describe Einstein-Rosen Bridges. These hypothetical constructs connect two distant points in space-time, forming a tunnel whose entrances resemble black holes. If such bridges could exist, they might allow a spacecraft or even information to traverse immense cosmic distances in an instant. Bypassing the millennia it would take with conventional propulsion. Yet the practical challenges are staggering. Ordinary black holes formed from collapsed stars are incredibly hostile environments. The intense gravitational gradients near the event horizon would spaghettify any object, stretching it into a thin line of matter. Radiation emitted from the accretion disk can obliterate spacecraft long before reaching the singularity. And there's no evidence that a natural black hole connects to a distant region of space. Most likely it is a one-way trap. Some theoretical models suggest that rotating or Kerr black holes could provide more promising conditions. Their unique space-time geometry creates regions where stable wormhole-like passages might exist. Exotic matter, negative energy, or other yet undiscovered mechanisms would still be needed to stabilize such a tunnel, preventing collapse under the immense gravitational forces. Even then, a journey through such a gateway would push physics to its limits, bending time, warping space, and exposing travelers to extreme relativistic effects. Despite these dangers, black holes remain a beacon of possibility. They are both the ultimate destroyers and the potential gateways of cosmic exploration, hinting that our universe may conceal pathways far beyond the familiar Milky Way. By studying their physics, humanity glimpses the tantalizing edge of intergalactic travel, where imagination, mathematics, and cosmic reality converge in the pursuit of the impossible. Engineering the impossible as humanity dreams of leaving the Milky Way. The stark reality of engineering such a journey comes into sharp focus. Current propulsion systems, chemical rockets, ion drives, even the most advanced nuclear thermal concepts are painfully inadequate for intergalactic travel. To reach even the nearest galaxy in a human lifetime would require speeds approaching light itself, an achievement far beyond today's engineering capabilities. The energy demands alone are astronomical, surpassing anything Earth's power grids could provide. Containment, navigation, and life support pose equally daunting challenges. Shielding a spacecraft from cosmic radiation over centuries, ensuring supplies for multi-generational crews, and maintaining stable artificial habitats would demand technologies that currently exist only in speculative theory. Even robotic probes would face unprecedented hurdles, relativistic hazards, communication delays spanning millions of years, and the relentless drift of interstellar dust that can puncture hulls at near-light speeds. Yet where physics imposes limits, human imagination pushes back. Concepts once relegated to science fiction, warp drives, space-time manipulation, and traversable wormholes offer tantalizing glimpses of possibility. A warp drive, theoretically, compresses space ahead of a vessel and expands it behind, allowing faster-than-light travel without violating relativity. Space-time manipulation, still entirely speculative, suggests the ability to fold cosmic distances into navigable shortcuts. AI, with its capacity for rapid calculations and autonomous problem-solving, could become the navigator, engineer, and overseer of journeys too complex for humans alone.